Next talk will be by Thomas J. Finn, who will be talking about pushing Cython to its limits in Scikit-learn. Thomas J. Finn is a senior machine learning engineer at Union AI and a maintainer of Scikit-learn, an open source machine learning library for Python. He led the development of Scikit-learn's set output API, which allows transformers to return pandas data frames. Previously, Thomas worked at Columbia University to improve interoperability between Scikit-learn and AutoML systems. He also maintains Scorch, a neural network library that wraps PyTorch. Please welcome Thomas.
Hi everyone, welcome to my talk, pushing Cython to its limits in Scikit-learn. The material for this talk is available on GitHub. If you scan the QR code, you get to these slides. It's our HTML page. There'll be a lot of links to different places. So if you want references to things I talk about, feel free to take a picture. I'm going to show it again at the end of the talk. So, who here has used Cython before? Okay, good. Yeah, this is for you. I don't know if there's many of us, but this is for you because we push in Scikit-learn. We use Cython extensively, and we, as I said, we push it to a limit, which I don't know if I'm happy about, but that's what we do, and I'll talk about it. So, but it works. So let's go to the slides. So a little about me. I'm a machine learning engineer at Union, where I work on an open source project called Flight, which is a workflow orchestration engine. But today I'm wearing another hat. I'm wearing my Scikit-learn hat. I'm a maintainer for the project for around 5 years now. And like a lot of this talk is based on my experience working on the project with Cython, reviewing pull requests in Cython, and how we use this language to optimize Scikit-learn itself. This is the agenda. I'm going to start with why Cython for those not initiated, for those to get why we choose Cython and Scikit-learn, a brief overview of what Cython looks like, and then majority of my talk is at the end as the use cases like Scikit-learn. So a lot of this is code examples from Scikit-learn so that you can see how a library like Scikit-learn uses Cython in a production code base. So I'm going to drive this by using tons of examples. Yeah. So let's start with why Scikit-learn. Why Cython? This is the two major reasons. It's Python-like. It looks like Python when you read it. Most of the time we go down to Cython, which is a compiled language, because we want to improve runtime or improve memory usage. It's either one or the other or both. So some of the examples of things that we've done in Scikit-learn where we use Cython and some of the numbers. Well, our history grading boosting is we wrote this around 4 to 5 years ago. It's a Cythonized version of like EVM, which is C++, and when we developed it, it gave the same performance, equivalent performance as like EVM. When we refactored our loss functions, because in machine learning, lots of time you're optimizing a loss. So when we moved that to Cython, it improves everything that uses loss, which is linear models, the gradient boosting, classifier regressor. So that was an improvement. Furthermore, we had around a 20x improvement in all of these modules because we Cythonized pairwise distance reductions. It's a thing you do when you have to compare points in a data set, and that happens in all these modules: cluster, manifold, neighbors, semi-supervised. When I worked on target encoder, when I first developed it, it was first in Python, and I was like, well, I could get this a little faster, so I rewrote it in Cython, which is around 150 lines of code. It was at 4 to 5 times extra time improvement compared to my Python version. And I also had less memory usage. So these are the things you get from using Cython. The last bit is there's validation checks everywhere. And when we switch this over to Cython, it reduced memory usage. And we'll go over some of these in these slides, but this is like the slide. So this is why we do Cython. So which is very nice. So when we talk about any type of performance optimization, we have to talk about profiling. So you have to, when you want to optimize any code, you have to profile, find what the hotspots are. Scikit-learn is a mixture of Python and Cython. We don't optimize everything. We only optimize the spots that make sense. So these are some of the profiling tools I use. cProfile, VizTracer for finding where the hotspots are, what functions are running the longest. I also use Memray for memory profiling and scaling for some. It's a mixture of memory profiling and non-profiling. I won't go too much into this, but there's many tools. So I recommend you finding, if you want to do any type of optimization, profile your code. So Cython 101. So this is what Cython looks like, and what it looks like to develop with. So what I'm going to cover here is Cython compiling, with the very simple minimum example. Then what types look like in Cython. Because Cython is a compiled language, it converts your Cython code to C and then compiles that. That's what Cython does. And so having types makes it so that compilers understand the types coming in, which means there are benefits, which I'll talk about. And then lastly, I'll talk about some development tips, some the ways I develop with Cython and how to be efficient and working in the language. So this is the simplest example I could think of for Python for compiling something. This is, I call this simple. It adds two numbers. The way you compile it is you introduce a setup.py. Who here has wrote a setup.py before? Okay, good. This is, I guess, for you. So you could write this. You could compile your it's called simple.pyx by running a build command. And all this does is this is all the boilerplate you need. When you run this command, you get this module called simple. You go import it from Python and you run it. That's it. Okay, that's all. That's like the bare minimum example. And remember what the code looks like. It looks like that. It looks like Python, right? You compiled it, and in this case, there's no types or anything. So the only thing you get from here is that you don't have to go to the Python interpreter anymore. It doesn't have to read the byte. It doesn't have to interpret what's going on. It's a compiled extension, and it's fast in that extent. But you could do more. This is just bare minimum. What makes Cython special is that you could introduce types. So here I'm adding ints. So here I have two ints, and so I'm telling Cython that these types will have to be ints. I can't pass strings into here anymore. And so this optimizes for adding two ints, compile it, and it works like before. And this now you allow the compiler to specialize on types. So this is essentially the superpower of Cython. You can add types to your data, and your code works better because you have types. That is like the overarching view. More about the syntax, you can see that I use def here. Def means that I could call this Cython function from Python. So this is, if you want to expose it to Python users, you use def. If you want to write many Cython functions and call it within Cython, you use cdef. So you're defining these are Cython-defined functions, and you cannot call these from Python. So for example, this is a linear function. It's cdef, so I can only call it from Cython. It returns a float, just like any other compiled language out there with types. And I could call it like so. So I'm calling this from a Cython function. You can see that I also could use cdef to define types, just like in C++ or Rust or C. And so this is all allowed in Cython. There's one note here. There's something called cpdef. Cython uses this just like def, but I do not recommend using this to call from Cython. So cpdef allows you to call from Python and Cython, but I don't recommend you call it from Cython because it's a performance hit from doing this. So I never use this. In Cython we use this, but we use this just like we do with this one. So that's the three ways. When developing, one of the key things in Cython is I like using annotate. Annotate allows you to have this view of your code where yellow means there's Python interactions And the whole goal of this game, once you have this annotate mode, is to remove all the yellow. Like do stuff to remove yellow and code go faster, right? So, which is, it's a nice game, it's a nice game, and it works. Like, yeah, you just move the yellow, things go faster, and the way you get it is you have annotate. You run annotate on your function, on your module. So you can also, for those who like working in Cuban notebooks, you could do exactly the same thing in a Cuban notebook. You have a magic, do load Cython, and then have this double ampersand Cython, and all this will be compiled. And then this function called toLinear will be available in your notebook environment so that you can mess with it. You can also do annotate in a notebook environment. So like you could just iterate on your Cython code in notebooks. So until you get it right, till all the yellow goes away, right? So it's a very nice experience. So that is this is working with this is development. So that's now I'm going to jump to the bulk of this talk, which is Scikit-learn use cases. Scikit-learn has many use cases, but we're going to cover the Python to Scikit-learn interface because when you deal with any compiled language, interfacing with Python means you have to go between the two languages. You have data in a Python that's wrapped around a Python object, and then you want to send it over to Cython and then do stuff with it and then send it back. So you run across this problem all the time with any compiled language when you integrate with Python. Like you write C++, you write Rust, C, well, those are the three major ones. You have to think about this. And then, so I'll first go into that, and then I'll talk about some performance techniques we use in Scikit-learn to improve runtime or memory usage. And they get more and more advanced as they go on. So it's gonna pick up steam, so to say. All right, so Python Scikit-learn interface. Scikit-learn deals with numerical arrays. It's a numerical library. It deals with NumPy arrays normally. So it's designed around NumPy arrays. And the way we pass NumPy arrays into Cython is, well, a memory view. And this is a syntax where it's a very simple syntax. So this thing is a two-dimensional array. The way that you signify it is with this brackets with double ampersand. That's two-dimensional. If you have three of them, it's three-dimensional. You have four of them, it's four-dimensional. So that's it. So once you have this syntax, from Python, you could create an array. In this case, it has to be two-dimensional. And then if I could pass it in here, once I compile it, I could pass it in, and this works. So that's it. That is how you use memory views to transfer data from Python to Cython. And the neat thing about this function, add value, is that, this is using the Python buffer protocol, which is a standard from Python that we use to pass the data around. The neat thing about this add value is that you could start writing loops. And like normally in Python, people recommend never to do this, but in Cython you can. It's fine because it's going to be compiled down, and then you could write loops with your two-dimensional arrays, and everything is fast because it's going to be compiled down. So it's very nice. It's very useful. So I'm writing loops. I'm just adding a value to an array. This thing looks very Python-like, so that's why it's very approachable. This is like you could write Python-like things and get the performance that you want. And it's okay. So that's just very nice. You also see this. There's APIs like .shape to get how big this array is, so you could index to them. So for memory views, the thing you optimize for memory views is we use directives. There's a lot of them. This is the Scikit-learn directives. I'm going to cover some of them. And directives are things you could instructions for Cython to do certain types of optimizations or remove certain checks. So I'll cover a few of them so you can get a good feel of it. So first one is bounds check equal true. This is by default. And this is when you have an array and you pass an index that is not in bounds. Cython will do this check for you, and that adds overhead. So if you're sure that your bounds are correct, and you can see here, if to annotate, there's some Python, there's like a big box of Python code, and then it raises an index error because If it's out of bounds, it rates index it. That's very Python-like. But if you're sure that your indices, when you write your code, that it's in bounds, you could write bounds check false over here. It's always over here. And that means that the whole block of code you just saw when I did annotate, here it's all gone. And it's not yellow anymore. You see this is now white, which is good. So this means that we're not allowing Cython to do that check over and over again. And this is very useful when you do loops. Remember that code I had with 2 loops? Imagine you're doing the 2 loops and you're checking every time. That adds overhead. So this is a good strategy to use if you know for sure you're writing good code and you're never going out of bounds. Another version of another directive is called wraps around. So wraps around is a very Python-like thing where when you call -1, it goes all the way back to the beginning. This is, and you can see it's the code over here. So it wraps around literally, and this is another check. It checks if it's negative wrap around. You can also remove this as well by doing a decorator, this Cython that wraps around false, and this would turn that off, and you see that the code from above, like over here, this box here, if I annotate that, it's gone. So these are there's many of these directives, and like these are things you just need to know if you're working memory use and you want to optimize for performance. Okay, so these are setting it in a directive, and you can see that the way I grab this directive is I'm using C import. C import means I'm importing from, it's a Cython version of importing things, and so I'm C importing this directive, this direct decorator, and then wrapping this function. But this may be, if you have many of these, it could get very annoying. So you could also specify at the top of file, so you have it for everything in your file. In Scikit-learn, we push this to an extent where we do it in our build backend. We use Meson. Who here has built a compiled library in Python? Okay, cool. Meson, one of the build backends. It works. It's fine. There's a few of them. I'm not gonna talk about it, but it's good. It's good. It works. But we do it globally. We have a build backend. We put these directives globally so that we don't have to put these directives anywhere in Scikit-learn's code base. It just does it globally. And one of the cool things that we do is that we make bounds check configurable in the build system. That means, because bounds check is, if you don't check the bounds, you go out of bounds. So in CI, we turn this back on so that we run through our tests, we do bounds check, and so that we know if there's invalid code somewhere. But when we ship it, we turn it off. So it's a cool strategy, and and this is what we do in Scikit-learn. Okay. So memory views, that's how you have directives in Scikit-learn with memory views. The next bit is returning memory views. And this is an isotopic regression. I don't normally recommend returning memory views. So this is XOut thing XOut object is a memory view, but normal Python developers don't know what to do with these objects. So I would always wrap them around in an array, a NumPy array, so users know the users are familiar with NumPy arrays. So I always wrap it around. And using as array on this memory view is a no copy thing. So it doesn't copy any data, it just wraps it around and sends it back. So it's very nice. So memory view. Isotopic regression, also core algorithm. Okay, when we're talking about memory views, I will also want to talk a little bit about strides. Who have seen strides before with like 2D-dimensional data? Okay, for everyone else, strides in 2 minutes or 1. This is a memory buffer from 0 to 11. Right, this in memory it looks like this. There's 2 ways to view this if you look at 2D-dimensional data. You can look at as a row. So this is called C continuous, and then you can specify this Cython with this double, like the upper double ampersand 1. So this signifies that the data is stacked up as a row. The other way to view this is the stacked up column rowing. And this matters a lot when you do data access. So if you have an algorithm that if it's C continuous and your algorithm goes through this way, that means it's very quick because if the data is right next to each other in memory. But if you try to do it the other way, this is slow because you have to jump in memory to get to the next element. So same in the opposite logic for the other side. So it's when Scikit-learn, we do pay attention to this order when we write our algorithms because it's fast in one direction and slow in the other direction. So, and then there's a way to specify this in Cython, like that. And then so if you put the double dots in the first spot. And a common theme, in NumPy, there's a way to figure out what type of continuous you have. By default, if I create a NumPy array with any of the creation tools in NumPy, you call dot flags. They're C continuous by default. So NumPy creates C continuous things by default. You could change it by specifying the order, but this is NumPy. That's how a user knows what order they have. Now this is a topic around strides with 1D things. Like 1D things, you think like, there's no such thing as strides, but there's this. You still have to think about strides in 1D dimensional arrays, and this is how. Let's say I have this C continuous array. If I look at a view of this on the first row, this is continuous because the data is right next to each other. So I can specify a view. This is selecting the 0th row, and this is C continuous. But and the way you specify is using the double dots again and with a 1. But if I go the other direction, it's a one-dimensional array, but it's not continuous anymore. So this is the example of having a one-dimensional array that is not continuous. And you may not. So this may happen if you have user input and you have no idea what continuous, how continuous. Like they may have sliced their NumPy array in this form. Let's say the one index column, and then you don't have no idea. So you have to write your Cython code with no assumption about continuous legality. So that's strides with 1D. So there's a lot of fun things with strides and memory view, but these are the ideas. We also have const memory views. This is working. This is in k-means and bisecting k-means. And so this is it's stuck a constant here, and that means it works with read-only memory views. So that means you can't write to this x. You can write to x, you can write to sample weights. And this is very useful in context of how we do multiprocessing in Scikit-learn. So this is an example of having search CV, which is a multiprocessing, which we do successive having, it's a hyperparameter search. We do use multiple processes. And what we do here, if the data is big enough, is that we write it to randomness in read-only mode, and all our workers will reference this data. So so this is an optimization we do, so where we need read-only data, and this is one we do. Const memory views, structs. Who here has written C sometime in the past? Okay. These are C structs, basically. Right? C struct, C def structs, it's a C struct. You could use them like a struct, you could use them in combination to many things. You could use, in this case, I'm using a stack from C++. So you can import C++ things from Cython. And then in this case, this code is doing def registers for pruning. I just chopped it off. So you can see that I could create a stack of these things. I could push with this like dictionary syntax too, and it works. It's very nice. So you're working with like C++ level constructs, but with a language that looks like Python. And this is used in tree and random forests. There's also something called packed structs, which means that your data is right next to each other in memory and not aligned. I won't go too much into this, but the idea is we have packed structs for memory views because in NumPy has structured D types. So this representation of this type is the same as this representation as in C, and this allows you to interact with Python using a structured D type. And structured D types are nice because you have an array of these named entities. So it's very nice to work with. And so that's why we have packed memory views. And this is in our history grading boosting algorithm. Cython I call them Cython classes. These are extension types. So here you have a CDEF class. This allows you to instantiate, create objects in Cython that you could instantiate in Python. So here you have some, and furthermore, the elements inside of this tree object could have pointers. This is not a Python concept. This is it's like a C-level concept. You could have them. And so you could define these things in Cython, and you can initialize them in Python and use them. So you're defining something in Cython that you could use from Python. And the way you do this is that this is used in our tree algorithm for forest gradient boosting. And the way you do this is that we have a C init. This initializes the tree because there's like pointers and whatnot. You can't do it. We don't know. Like you have to write not Python to instantiate. You have to write something else to instantiate these pointers, and we do. We have like an alloc to allocate the pointers, and then we also have a dealloc for freeing them. This is a very C++-like concept, like where the object creating these pointers are also responsible for freeing them. So it's very nice. So this is also in our tree algorithm. So that's how we structure things. Like we have memory views for passing data around. We also have ways to create objects in Cython, defining objects in Cython and have them being accessed from Python. So that's the communication, the interface between Python and Cython. Now for performance, we do a fair bit here. The first thing when we talk about performance in Python is the GIL. The GIL is who knows about the GIL? We're in a Python conference. Everyone knows about the GIL. I hope. Okay. So the GIL prevents Python objects from being accessed at the same time. And this essentially prevents you from doing multi-threading in Python. But the solution to this that many numerical libraries have used is releasing the GIL. And how do you release the GIL in Cython? Releasing the GIL. And releasing the GIL, if let's say this is code taken from training a random forest. This function here, parallel build trees, is a function that mostly releases the GIL. And that means that we could call this in parallel using multi-threading, and this would use up all your CPU cores. And this only works because parallel build trees, the Python function, releases the GIL most of the time. And the question is, how do you release the GIL in Cython? It's a context manager. That's it. Like you just do this, and the GIL is released for this block of code inside here. And the thing about the block of code inside, it cannot interact. It can't hold on to the GIL anymore because you released it. And so you can't interact. You can't interact with Python objects that require the GIL. And so you can see here that I'm calling all these are usually C-level objects, and I'm calling methods here to index context manager. For one example, I have one method called a splitter because I'm splitting a tree. I'm splitting nodes in a tree. Node value is a method of a splitter, and the way we define this node value definition, this method, you see that there's a no GIL here. And this no GIL at the end means that this function can be called in a no GIL context. So you could use it in a no GIL context. And so this is how this is set up. And so that's releasing the GIL. There's also another example is checking for infinite and nans. So generically, if you have a big NumPy array and you want to check if there's nans or infinities in it, this is how you code it. You do a isNan and then a any. But let's say X is like a really big matrix, all right? This will create a big matrix of booleans. And so that means you're instantiating an array as big as your input. And this is overhead, this is memory pressure. And so the way we optimize this in Scikit-learn is we have a isInfinite check in Cython. And it just loops through the array, and then we early exit with an error code so that we could check it without making the copy. We also have OpenMP parallelism. Here, you use C input to input the C input P range. And so this internal here, this is a binary search. And writing P range instead of range here means I parallelize the insides of this function. And that's it. You just change this range function to P range. You can tell it how many threads you want, and it will parallelize everything inside. So, which is very nice. It's very Python-like code that you can easily parallelize with OpenMP. We also call SciPy blast from Cython. You can see import things from Cython blast. This is general. This is matrix multiply, and the way and then you can use it. And so one of the ways we use it is that we use it in combination with OpenMP. So this is using p-range here, and then internally this uses the general matrix multiply, so that we're using a blast function. We're using OpenMP for parallelizing, and then for each thread, we're calling a Cython blast function, which is the optimized version of matrix multiply. So we could like mix and match these things together. So this is in k-means. This is like a quick overview. Like this is there's a lot, I guess. So this is next is C++. I already showed you stacks. This is for maps. You could use dictionary instead of using a dictionary for going from ints to floats. We write a wrapper around ints to floats, and this is a C++ map. And so this dictionary only works when the key is an int and the value is a float, but it's fast. So this is why we do it. And we do it in, and we can add methods to it, and we do it in this clustering algorithm. So that's one version, that's just using maps. We can also have vectors. We can use C++ vectors. So this is using C++ vectors, and this is like C++ API, push back, size, pop back. These are all C++ algorithms. This is using DB scan. You can use vectors. A fun one is that we can have vectors or pointers. So vector pointers means that I could access data without Go because they're pointers to things. And this allows, so using a vector pointer allows you to access data without the Go, because these are not Python objects, pointers to data somewhere in memory. So this is also another technique we use in Scikit-learn. This is in target encoder. C++ algorithm, you could use the C++ algorithm. We have used like heap q from Python import module. So this is the same thing, but in C++. It's the same type of API. You have a pop, heap, and push heap, and you just do it. You have a different syntax, but it's the same idea. You have a vector thing, you can treat as a heap. Okay, fuse types. This is we use it everywhere almost. Fuse type is a type that could represent two different types. So this is something in Cython that's defined in Cython. It's a fuse type called floating, and it could represent a float or a double. It's already defined in Cython, so you can see import it. And this means that when I define this function called max, absolute max, floating represents both a float and a double. So this generates two functions, one that works on floats and one that works on doubles, but you only wrote the function once. So which allows you to support multiple data types. And so this is a simple example of using finding the absolute max. You could even push this further and define your own fuse types. This is like an int one that supports 64 and 32-bit ints. This is a one that supports ints and floats. And then you can have this in function definitions, and this defines 8 functions, because you have 2 there and 4 here, and you have to have all the combinations. And so you write this function once and supports all these C types using fuse types. So it's very nice for fuse types. For a fuse type, you can also, so this is a vector. You could have a vector of a buffer. You have a vector in C++. You can return as a NumPy array, and you wrap it in Sentinel, and you can return as a NumPy array. So that means you can write a vector and then return NumPy array that's a view into the vector using a Sentinel. I won't go into detail, but this is the idea. So it's very nice you can work in C++ vectors and then return as a NumPy array. We got fuse types and classes. That's a thing. Tempita, and this is code generation. In some places, we need code generation because you can't have fuse types in when defining elements in a NumPy and a Cython class. So code generation. I'll show you an example. Here, this is like a template. We use code generation to generate both of these. All right. So there's a 64-bit version and a 30-bit version, and that's what we use Tempita for. And we use this in loss functions. I won't go too much into this, but we use this because we want to optimize for, when we generate code, means that we want to inline things and make things go faster. That's the arching goal of this performance optimization. So I want time for questions. So this part is we covered a lot. It went pretty quick, but we covered there's lots of Python decided interfaces and lots of things we do in Scikit-learn for performance reasons. Remember, like these are the ideas we talked about. Like this is the reason why Scikit-learn does performance. All these benefits we get. But yeah, so that's my talk, pushing Cython to its limits. This QR code has slides and materials online. Check it out. Thank you all for listening. Okay. Yes? Hi.
Great talk. Few questions. Floated, thank you. Float and integer overflow. So how do you deal with, right, in Python you don't care how big the number is. In C, if it's over 32 bits, you're starting to run into problems.
Yes.
Do you have to deal with that?
In Scikit-learn, it will overflow. So you have, and that's, so yeah, it will overflow. And so when people get their models, they will see infinites. And if we try to optimize this away, it adds performance overhead, so we don't. So we're hoping that people, when they look at their models, they're like, this is a bad model. Right? So we don't deal with it. We don't check for overflows because that adds too much overhead. Yeah. So.
Wow. What about garbage collector taking care of memory leaks? Like, how do you test that you don't have any memory leaks in your code?
This one's harder. Recently, we've been adding free threading support, so that helps with. Free threading is Python removing the GIL, by the way, and that's actually we don't really test too much for it. Now I think about it. Yeah.
Relying on a user to tell you, right? I've seen a few libraries where just like we use them a lot for inference or something like that. It's just builds the memory over time, and at some point they fix it. Okay, good.
We get bug reports, and that's how we know there's memory leaks.
Thank you.
Are we done? We can go. Depends how much time you have. 2 minutes? Yeah, just have one more.
Yeah, I was just going to ask about the interface. Like you had mentioned that when you go between like C++ vectors or NumPy arrays, like you're not copying. Say something more about that.
That I just went really quickly. So this was a clever is it a hack? A clever way to do this, where when we call this NumPy API, we pass it the data pointer to the vector, which is a continuous bit of block of memory, and then so that we're not copying, we're just pointing to it, and then we tell NumPy that this is your base object, this Sentinel thing that wraps this vector, and that's it. And that means so there's no copy of data now. And then when the NumPy array gets garbage collected, the base object will also deallocate, and which deallocates the vector. So we had to wrap the vector in a Python object, and a Cython object for this all to work. I don't know many libraries that do this. I think we're one of the only ones that do this. So, right, thank you.